All right, so we'll get started here. So I just, here's a list of all the problems I'd recommended from section 7.5 and 7.6. There's a chance I never posted this, like maybe I wrote it on my file at home, but I never posted it. If not, if so, I'm sorry. Anyway, to end the mystery, 7.6 I've just assigned 5, 7, and 29. All right, so anyway, so here's a list of problems I'd like to solve in today's video, and let's get to it. So I guess I should just take a second to, here's where we're going. I'm trying to solve all of these, then these guys down here. All right, so here's the first one, section 7.5. Number 10, I'm trying to solve cotangent of x plus 1 equal to 0 on 0 to 2 pi. Alright, so you know what I'm going to do? I'm going to change this to a tangent problem because I prefer tangent. So this is the same as cotangent x equals to minus 1. You know what? It's probably good. We haven't graphed cotangent too much. Let me go ahead and graph the cotangent. So let's see here. What's cotangent x equal to? Well, cotangent of x is sine over. That's tangent. I'm a dummy. Cosine over sine. So the places where cotangent's not defined is wherever sine has a 0, right? So remember, sine of x equals to 0 if and only if x is an integer multiple of pi, right? So if we're just looking at 0 to 2 pi, right? So 0, and then over here to 2 pi, right? So 0 is a vertical asymptote, right? And pi, right in the middle, is also vertical asymptote, right? So you got these three places. Now, of course, 2 pi is not included, but I'm just drawing it and putting there for the sake of context. Furthermore, we know that the graph, it goes through 0 when cosine 0. Well, that happens at pi over 2 and at 3 pi over 2, right? Now, this is quadrant 1 basically, between 0 and pi over 2, so cosine and sine are both positive there. So that means it's got like a vertical asymptote like that. It goes through 0, and then in quadrant 2, which is between, quadrant 2 is between pi over 2 and pi, right? And pi over 2 and pi is exactly where we are when we're here, right? Well, there, in quadrant 2, we have the x values are negative, which means cosine's negative, and sine's positive, so that gives you a net minus, and then this story kind of repeats. All right, so in quadrant 3, you have sine and cosine both negative, so you get a positive. And then in quadrant 4, you've got sine negative and cosine positive, so you get negative. Okay, so that's the graph of, that's y equals cotangent x, right? All right, so you notice that cotangent x has period pi, right? So if we find one solution, we find another by just adding pi or subtracting pi. And so the solutions, we're looking for equal to minus 1, right? So that's something like this right here, right? I'm probably not doing justice to it, but there's y equals minus 1, right? So how can we get cotangent equal to minus 1? All right, so if I'd drawn this better, you can easily, we should all know that the cotangent of pi over 4, which of course is 1 over the tangent of pi over 4, right, is 1. So that would be like here, right? So by symmetry, if I'd drawn this better, we should have minus 1 over here, you know? So apparently, what's halfway between pi over 2 and pi? 3 pi over 4, right? So I'm pretty sure cotangent of 3 pi over 4 is equal to minus 1, right? Now, notice that that's also equal to 1 over tangent of 3 pi over 4, right? So we could check our answer by calculating, we can check our answer by going to our handy-dandy calculator and plugging in tangent of 3 pi over 4 if you're in doubt. I'm in radian mode, good. Checking on that, always check on that. Pi divided by 4, we got minus 1, right? So tangent is minus 1. Notice that 1 over minus 1 is minus 1, so check. That's one solution, right? So we have one solution right here. Again, my graph isn't quite right, so that should be at 3 pi over 4. And then you add pi to that, right? Because of the period pi, right? And what's 3 pi over 4 plus pi? Well, it's 7 pi over 4, right? And that's it. That's all the solutions you get. So therefore, answer is 3 pi over 4 and 7 pi over 4. Those are the places from 0 to 2 pi, which gives you a cotangent of minus 1. So again, I take a strongly graphical approach, right? And if you're uncomfortable with cotangent, you could have traded this problem at the very beginning. That's what I was thinking about doing. You know, alternative approach. Stupid marker. Can't draw. So alternative approach here would be trade your cotangent equal to minus 1 is the same as 1 over tangent equals to minus 1, which is of course the same as tangent equal to minus 1, right? And then just to give you a lightning speed tour of that solution, it looks something like, well, tangent does this, right? Whee! And it's got that pi over 2, right? 3 pi over 2. And so when you go through minus 1, oh, I've not drawn the tangent correctly. See, this is why you shouldn't hurry. So what's tangent look like when you draw it correctly? Dummy. Alright. So it's got vertical asymptotes here, 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 right? And the graph of tangent, it's like this, right? Where this is at pi, 2 pi, etc. So, of course you're going to get the same solutions, right? But you get them from this intersection point with the tangent and that intersection point with the tangent. So if you're more comfortable with graphing tangent, you can switch this to a tangent problem. And perhaps that makes it easier. I mean, notice that inverse tangent, you could straight up calculate that on your calculator. I don't think you have an inverse cotangent function on your calculator though, do you? See, in this way of thinking, we could have done inverse tangent of minus 1, and that would have gotten us the, look at that, minus pi over 4, so you'd still have to think about it. You have to add pi to that, right? So that would have given you the first, and then you can add pi again to get the second one. See, the calculator is giving us this guy back over here when we took inverse tangent of 1, right? Minus pi over 4. Anyway, all right, enough on this problem. Let us move on. I'll try to go a little bit faster through the future problems here. Otherwise, this video will take forever. All right, number 21. Oh, all right, fine. Section 7. This is kind of like one we did in class that had a bunch of answers, but I think it's probably good to go through another one. So I'm just going to take my medicine and do it. So we're supposed to solve 2 sine of pi theta, right, plus 1 equal to 0 on 0 to 2 pi, right? So the first thing to do is to figure out what's the period of this guy, all right? So so this thing goes full cycle, right? When 2 pi equals to pi theta, right? So this means that theta equals to 2 gives full cycle, right? So that's the period of this function. Now we're trying to solve what? Our goal is to solve, let me take this equation and rewrite it a little bit. This to solve the sine of pi theta equal to minus 1/2. I think that's easier to think about. Then all we got to do is graph the sine pi theta function, and we can then look for intersection points, right? And of course the calculator can help us a little bit. So notice that 2 pi, this is, you know, like numerically, this is roughly, well, the 0 is exact, but this is 6.28-ish. All right, so we're going to get 3 full cycles of sine, and then just a little smidgen of the next one. All right, so when we're at 2, 4, 6, right? And so sine looks like what? It looks like this. So that's roughly speaking the 2 pi. Again, 2, 4. That makes this 1, 3, 5. All right. See, because if you put in any integer, then sine of pi n is 0, right? So 0, 1, 2, 3, 4, 5, 6. These are places where the function y equals, you know, sine pi theta is equal to 0. All right, so we're trying to find where that is equal to minus 1/2. So I should have made that graph bigger. Oh well. Anyway, here's a picture of it. So basically we're looking for intersection points between these two things, right? And so we can use the calculator to find one at least, right? I mean, let's do that. Why not? Inverse sine, but then we have to think about what to do with it. Minus 1 divided by 2, what does it give us? So this tells us that sine inverse of, now I gotta be careful with this, right? Sine inverse of sine of pi theta. Don't be tricked here. Let me show you how we gotta be careful. This whole thing gives us pi theta, not theta, right? So beware of that. So this gives us pi theta equals minus pi over 6, right? So this gives us the solution theta equals minus 1/6. Now that does not count, right? That's not an element of the place we're looking for a solution, so we're gonna have to reject that. But it does help us, you know, if we just draw this graph a little bit back into the, you know, back here. That shows us that this point right here was like minus 1/6, right? Now, so there is the period of this function has period what? It has period 2. So I know that minus 1/6 plus 2, minus 1/6 plus 4, minus 1/6 plus 5, these will also be solutions because it repeats itself, right? And those ones are this one, and this one, and this one. All right? And you can see, by the way, that past 6 we don't get anything because it's not going to intersect minus 1/2. All right, so if you do the arithmetic here, you know, 2 2 minus is sixth is 11 sixths. 24 minus 1, 23 sixths, I believe. 30 minus 1, 29 sixths. So these are half of the solution set, right? I'll do the other half in a different color. Let me go up a little bit here. So now if you look at this right here, right? That's the other kind of solution. So like how do we, you can focus right here. If I draw this graph bigger, it would have been helpful, but there's like a symmetry, right? This solution, which was what? 11 pi over 6, right? Excuse me, it was 11 sixths. Forget about that pi, 11 sixths. Well, that is 1/6. There's like 1/6. See here to here, this distance, 1/6, right? So the same way over here, distance from here to here, should be 1/6 by the symmetry of the sine graph. So I see if I take 1 and I add a sixth, that should be a solution, right? And so if I take and add 2 to this, I get 3 plus a sixth, right? And then I add 2 to that, I get 5 plus a sixth. Again, I'm using the period 2 the fact this function is period 2, and that gives me 7 sixths. 18 plus 1, 19 sixths. 30 plus 1, 31 sixths. Those are my, apparently my answers. If I didn't mess something up here. And the, let's see here, 21. Yeah, the answers in the back of the book are 1/6, 5/6, 13, 17, 25, 29, 37. Shnikes. 30. What? Oh man. 1/6. Sine. Well, we'll just see who's right or wrong about this, won't we? I don't trust the book on this one. Let's check. Do these work? I take the sine. Proof's in the pudding, right? Let's check our own answer. So I'm going to plug in the 7/6 into here. So I do pi. Oops. Sine of pi times 7 divided by 6. I calculate the sine of that. Minus a half. Hey, look, it's a solution. Book is wrong. Book is wrong on the answer key here, my friends. See, you get what you pay for sometimes. But anyway, every first edition book has all kinds of errors like this. So, you know, if you don't get the answer in the back of the book, first thing to do is just check your own answer. See if you're right. See if the book is wrong. That's always a good thing to do with any book, honestly. Actually, it's kind of an important thing in life these days. Like, don't believe what you're told. Check things out for yourself. You can believe what I say, of course. But, oh, what do you know? These all work. It's almost like my solution's right and their solution is nonsense. Well, these all seem to solve. Uh-oh. What did I do there? 29 times pi divided by 6. I didn't get that one. That one didn't work. Let's try that again. Sine of 23 times, check this one again, pi. Is that one right? That one's minus half. But, so sine of 29 times pi divided by 6. 1/2. Really? Oh, well, no wonder. I'm an idiot. Look at that. Add 2, add 2. 4 plus 2 is 5. No, dummy. So that was supposed to be 36 minus 1, which is not 36 minus 1 is 35. 35 sixths. Well, see? This is why we should check our answer, because sometimes we make mistakes. 35 times, just as I planned it, of course. Let's see here. Minus a half. Okay, enough of this problem. It seems I've taken as long on the second problem as the first. At this rate, this video is going to be 2 hours long. Ay, ay, ay. All right. Solve. 7.5, number 31. Solve. 8 sine squared x plus 6 sine x plus 1 equal to 0 on 0 to 2 pi. All right. So what we do is we make a substitution. This is 8, let's say a squared, I shouldn't use a. 8y squared plus 6y plus, I usually use x here, but they already used x as an angle. Thanks a lot, book. Equals to 0. Now, how do you solve that? Well, there are various ways. I don't like the look of factoring. We probably can, it's a book problem. I believe in factoring, so I bet it factors. Let's try it. I mean, I'll try it. Why not? Oh, it's a good thing I tried because it does factor. Look at that. Otherwise, I could use the quadratic formula and make my life harder. But yeah, we should at least give factoring a try. See, 8 times 8, 8 times 8. Listen, 2 times 4 is 8. 4 plus 2, 6. 1 times 1. Okay, factored. So this says that 2y plus 1 equals to 0, or 4y plus 1 equals to 0. That's how we get solutions, which is to say that y is equal to minus 1/2. Or y is equal to minus 1/4, right? So we actually have the problem sine of x equals to minus 1/2, or sine of x equals to minus 1/4, right? That's what we have to solve here. Now, these are essentially, I mean, we just saw that this has solution minus pi over 6, right? If you take inverse sine of both sides of this equation, it will give you minus pi over 6, right? So like x equal to inverse sine of 1/2, minus 1/2 rather, is minus pi over 6. Now that's not the solution we're looking for, right? Not at all. But we do know that if we if we add 2 pi to that, then that still gives us a solution, because sine has period 2 pi. Now the adding 2 pi one, right? So minus pi over 6 plus 2 pi would be equal to 12 minus 1, 11 pi over 6. So that's going to be one of the solutions, right? And again, here you get x is equal to inverse sine of minus 1/4, right? Now that is actually, I mean, that's a number that's negative, all right? Here it is. I mean, I'll crunch it out for you. So minus 0.24. So this is not an element of 0 to 2 pi, right? But if you add 2 pi to that, because remember, sine is 2 pi periodic, that gives us an answer. So sine of minus 1/4 plus 2 pi is approximately equal to 6. Now the answers in the back of the book are not decimals, but I actually prefer decimals for these sorts of problems, honestly. I mean, the answers in the back of the book are, you know, typically in terms of inverse sines and such, which, I mean, technically they're more precise, right? But, all right, so let me just draw a picture of what's going on here. Let's try to get a full account of what we have or what we're perhaps missing, right? So sine, I'll put pi here, I'll put 2 pi over here. So I guess minus pi is like back here. So it's minus pi over 2. All right, so something like, okay, fine. Trying to do better than my last one, make it a little bit bigger. Especially since we're trying to contrast 1/4 and 1/2, right? So we are looking for the solution of, you know, so here's the, let's say this is y equals minus 1/2, right? So this is what the calculator gave us. right? And then we added 2 pi, so that gives us this one over here, right? So, of course, that is what? That is pi over 6 from there, which means this one over here, the other solution we're looking for by the graph, we should get also pi plus pi over 6, right? In other words, 13 pi over 6. So we've got this solution, we've got that solution, we've got this solution, and let me explain graphically that story there. So minus a quarter is halfway right here. And so, you know, that was the one the calculator gave us, which, you know, just to be explicit here, it's minus 0.247-ish, right? So if we add, we get over to here, this one, that was the one we already have. That's at 6.036, give or take. But the point is, this solution right here is as far from pi, right, as this one is from 2 pi. So we can take pi plus the sine, inverse sine of 1/4, and that should give us the other solution, right? And I think that's how the answer is in the back of the book, but you know, just to be more explicit, we get numerically, you know, 3.389-ish, something like that. So there's your 4th solution, right? So 4 solutions to this problem. All right. Did I get everything in frame? Let's see here. I think I did. All right, so what's next? Supposed to solve section 7.5, number 37. I have sentenced myself to solving 9 cosine, I'm just kidding, I love doing these, cosine 2 theta equals to 9 cosine squared theta minus 4. Ugh. Interesting. Alright, so if we could convert everything to cosine theta, we might have like a quadratic in cosine theta, which would be better. The question is, how is cosine 2 theta related to cosine theta, if at all, right? Again, we're supposed to solve on, they're so boring. It's always the same thing. Solve on 0 to 2 pi, you know, not included. So, great. All right, so. Well, you know, I don't have my formula sheet handy, but I do remember this. Cosine squared theta is 1/2. So this is like the one that's hardwired into my brain because you use it so much in Calc 2. So if you don't mind me just deriving, if I know this, then what? Solve for cosine 2 theta, what do you get? If you solve this, you get 2, multiplied through the other side, 2 cosine squared theta, right? Minus a 1. So there's how we can trade cosine 2 theta for cosine squared theta. And so what we have then is 9 times 2 cosine squared theta minus 1 equals to 9 cosine squared theta minus 4. Alright, so I've got an 18 on this side, I've got a 9 on that side, so I subtracted the 9 on the other side, and that gives me 9 cosine squared theta is equal to, and I have a minus 9 here, so I add 9 to both sides, I get 9 minus 4, right? So in short, I get cosine squared theta is equal to, apparently, 5/9, right? Which tells me that cosine theta is plus or minus the square root of 5/9, right? And so I can take inverse cosine of that. Excuse me, guys. But again, since I'm looking for all the solutions on 0 to 2 pi, you know, so one way I can make these problems easier on the test is if I just say, find a solution, or find 2 solutions, you know. But to find all solutions, I really don't see any other safe way around it except to draw the graph. So here we go again. I mean, if you find another way that you think, if the book has another way in it that you find convincing, go for it. But this is how I'm going to do it. So there's cosine. Square root of 5 divided by 9, that is approximately 0.75. So you're looking for basically the solution to this one and the solution to this one. So we can see there's going to be 4 answers if our context is 0 to pi, right? So this is 2 pi, and here is pi. That's where cosine's -1. Here is 0. I hope, if nothing else, all of these problems have sort of removed some of your uncertainty about how we graph sine and cosine. I mean, after about the 20th time we do it, it should start to stick, right? Now, if we calculate inverse cosine, remember, the range of inverse cosine is 0 to pi. All right, so if I calculate inverse cosine of 5/9, it's going to give me this point. If I calculate inverse cosine of -5/9, it's going to give me this point. So this is just straight up inverse cosine square root of 5 over 9. And this is inverse cosine of minus the square root of 5 over 9. All right. And then remember, cosine is 2 pi periodic. So what's that mean? That means that if we add 2 pi, we get over here, right? Oh, excuse me, that's not on the same part of the cycle, is it? So that wouldn't be the one. Oh, phooey. Actually, adding 2 pi doesn't help me. That gets me to the solution that's beyond where I'm looking. It's over here. And adding 2 pi to this one gets me to the solution that's like over here I don't care about. So adding 2 pi isn't going to help. Actually, I think they figure out both of these by symmetry of the graph, actually. And so what I'm trying to say is that this distance and this distance should be equal, right? So what that tells me is, how can I say this? That's true, but maybe a better way to look at it. Sorry, I'm slightly distracted. My children are singing in the other room, which is good, but not for my thinking. And anyway, so my point really should have been this. This distance right here is the same as this distance right here, but I know that distance. That's this, right? So I can say cosine inverse square root of 5 over 9 is an answer, but also 2 pi minus the inverse cosine of the square root of 5 over 9, right? And we also have inverse cosine of minus the square root of 5/9, right? And how to get this one over here? Well, let's see here. It's the same logic, basically. This distance, I'll call it d3. And this distance, d3, they're equal, right? So I can again take 2 pi minus the inverse cosine of minus the square root of 5 over 9. And I do believe those will be my 4 answers for this one, which we could give numericals for, but I'm being lazy. So let me check the answer on that one. Oh man, how's he got it? Well, they have 3 answers. I might have copied it down from the solution guide wrong, but he has 3 answers, and he's written in terms of inverse sine. So they chose a different path. Okay, great. How can we see? Well, I guess fine. Rats. I have no choice but to, in terms of comparing my answers to the book's answer. So I can do like cosine inverse of the square root of 5 over 9, right? So this would be the first one. So numerically, this is about 0.79. Well, I'll say 0.73. All right, fine. The next one, answer, no. Rats. 2 times pi minus the answer. 5.55, that's this one. Roughly speaking, right? Inverse cosine, wrong function, inverse cosine of minus square root 5 divided by 9. What do we get there? We get 2.41. So if I subtract 2 pi from that, that gives me minus, but it's minus what I want. So this one over here is 3.87. Wait a minute. Oh, I'm a dummy. What? How can... Oh, I'm sorry. I'm an idiot. That's this one. That makes sense. I was bothered by the number for a second. So those are the numbers I get. If I go to the back of the book and I look at the answer key for 37, they gave me like inverse sine of 2/3. Let's see if that's actually our answer in disguise. I get 0.729. Hey, look at that. Inverse sine of 2/3 is this one. So if you solve the problem a different way, you get that. And so, by the way, this is one of the reasons I like numerical answers for the test. Is you know, we can all agree on the decimal, even if we don't agree on our choice of inverse whatever. So anyway, I'm going to stop investigating. I'm just going to assume that I either copied the answer key down wrong, or in fact the book is wrong. There are 4 answers. There are 4 answers. All right, enough about that. So 37, 39. I'm going to stop checking my answers for the sake of time here, guys. So sorry about that. Sine t. Let's just hope I'm right? Solve on 0 to 2 pi, as always. Seems like I should give you some variety in that instruction. All right, so well, let's see here. The thing is, we know that, and again, there's a straight identity on your formula sheet. I just don't remember it. But I know sine squared t is 1/2 1 minus cosine 2t, right? So I can solve that for cosine 2t in terms of sine. And that's more than likely what they did when they got that answer they got in the last problem. But anyway, cosine 2t, cosine 2t, fine, I'll do an in-between step. This is 2 sine squared t equals to 1 minus cosine 2t, which then gives me cosine 2t is 1 minus 2 sine squared t, which I'm pretty sure is one of those identities we wrote down, right? All right, so we can use that to trade our cosine 2t for 1 minus 2 sine squared t equals to sine t, right? Well, great. Now we've got a quadratic in sine t, so let's let x equal to sine t, right? And that gives us 1 minus 2x squared equals to x, also known as 2x squared plus x minus 1 equals to 0. Because I believe in the niceness of book problems, this probably factors. Let's see here. So you got yourself a 2x on the one and x on the other. You got to put a minus 1 there, so but you want an overall, you want so you got to put the plus 1 here, so the plus 1 hits the 2, and you got to put the minus 1 over here, so you get 2x minus x is x. There it is. So this gives us either x is equal to a half, or x is equal to minus 1. And remember, x is what? Sine t. And, alright, go back to my handy-dandy graphical method. Here's the sine. So we're trying to solve. Get out of here. Get stuff stuck on my. Alright, so 1/2 looks like this. Right? So I know that that's pi over 6. Sine of pi over 6 is a half. So this is pi over 6 from pi, so that would be 12 minus 1, 11 pi over 6. Wait a minute. Pi is 6, so I should be making more careful. Pi minus pi over 6. So 5 pi over 6. Don't be a dummy. Me, not you. 5 pi over 6. And then minus 1, well, that's easier. I mean, sine t equal to minus 1. That only happens here, namely 3 pi over 2. Right? So, solution. X equals to pi over 6, 5 pi over 6, and 3 pi over 2. There you go. That is how to do that problem. And for what it's worth, that does match the answer in the back of the book. I just can't stop myself from looking at it. What's wrong with me? Alright, so section... Let me just double check that I actually put everything on screen there. Sorry about that. So this problem, and this was the solution. There we go. Alright, so number 41, I endeavored to do this one. Here we're solving tangent squared x minus root 3 tangent x equal to 0. Again, on 0 to 2 pi. Alright, solve that thing. Ah, very nice. See, this is tangent of x times tangent of x minus the square root of 3 equal to 0. So we can see from that we either need to have tangent of x equal to 0 or tangent of x equal to the square root of 3. Either one of those options will solve the problem, and those are the only ways to solve the problem. I will again take a graphical approach. All right. So here's my 2 pi, here's my pi, here's my pi over 2, here's my 3 pi over 2, and for the sake of symmetry, minus pi over 2. So we should remember vertical asymptotes for tangent are at half integer odd multiples of pi, namely like pi over 2, minus pi over 2, 3 pi over 2, etc., etc. And so you graph that thing, what you got? You got one of these guys, one of these guys, and so forth. Alright. Now, we're trying to solve tangent equal to 0. Well, that's easy. When's tangent 0? It's 0 here and here. Right? So this one, so tangent of x equal to 0 implies x equals to 0 and pi in 0 to 2 pi, right? The 2 pi we don't get to include because it's not included in the problem statement, right? And let's see here. Tangent of x equal to the square root of 3. Well, that's up here, right? Square root of 3 is 1.7-ish. It's a little bit bigger than that, so it's like kind of here-ish. I don't know. Square root of 3 is about like 1.8-ish, 1.7, somewhere in there. I think 1.7 something. All right, I gotta stop talking. Anyway, the point is there's a solution here, and then there's another solution here, and that one doesn't count because it's past 2 pi, right? Now, so we either get x is equal to the inverse tangent of the square root of 3, or pi plus the inverse tangent of 3, square root of 3. Now the inverse tangent of the square root of 3 I think is actually a thing. If I recall correctly, it is pi over 3, but let me check on that. Yeah, pi over 3. So we can summarize solution as x equals to 0, pi over 3, pi plus pi over 3, also known as 4 pi over 3. And there's your answers. So, yep, and that is the answer in the back of the book as well. That one was kind of fun, I think. All right, let me see if I can get the next page here. All right, so what's up next? All right, so we've got section 7.5, number 57. I'll try to do that one. It is 10 sine x cosine x equals to 6 cosine x on 0 to 2 pi again. All right. So this one's actually kind of similar to the last one. So I move everything to the other side, right? I get 10 sine x, because factoring is how to solve equations, like more often than not, okay? Because factoring allows us to, you know, divide and conquer. So this gives me, I can factor cosine x out as the thing, right? And then that gives me 10 sine x minus 6 equals to 0. So basically I either need to solve cosine x equal to 0, or I need to solve sine x equal to 6 over 10, also known as 3/5, right? Now cosine of x equals to 0, that we really shouldn't even need to draw the graph. You should really know this by memory, because otherwise, if you have to look this up or really reason, you're eating time that you maybe shouldn't be. But pi over 2 and 3 pi over 2, that's where cosine 0 on 0 to 2 pi, right? Now here, I'll draw a graph. Sine right, so 3/5 right up in here somewhere, right? So the calculator is going to give us that answer. Sine inverse of 3/5 is going to give me that's going to give me x equal to that. And then by symmetry over here, this should be x equal to, see the pi over 2 is right in the middle. Oh, but I gotta think, this distance here, right, is the same as this distance, so I could do pi, this is pi. I do pi minus sine inverse of 3/5, right? So that should be my answers, which I'll write in green. X equals to sine inverse of 3/5 and pi minus sine inverse of 3/5. There's your 4 answers to this problem. And those are all the answers, by the way. All right? And those are also the answers which are stated in the answer key. So there you go. All right, next up here, number 62 of 7.5. So here we've got 6 cosine squared x plus 7 sine x minus 8 equals to 0. Solve that. All right. So what I would do, I'd go, that's, remember, cosine squared x plus sine squared x equal to 1, right? So that means cosine squared x is 1 minus sine squared x, right? So use that to convert this cosine to 1 minus sine squared, see, because if I do that, then I've got a quadratic in sine, and once we have a quadratic equation in sine, we can make a substitution and solve this thing, right? So we let y equal to sine x, then that gives us 6 minus 6y squared plus 7y minus 8 equals 0. Let me clean that up a bit. Let's say that that's 6y squared minus 7y. See, I'm multiplying through by minus 1, right? Before I do that, though, 6 minus 8 is minus 2, so I'm going to get a plus 2. So I multiplied the equation above by minus 1 to get this. I believe in book problems being nice, so therefore I believe this factors. I could be wrong. At some point it's going to blow up my face, right? But let's try. I'm going to have to put minus 1 and minus 2, minus 1 and minus 2. So if I put the minus 1 here and the minus 2 there, that doesn't work because I get minus 4. Oh, that does work. Minus 4. Man, I just can't lose. I just can't lose today. All right, so eventually you're going to hit a problem where you got to use a quadratic formula or something, but not today. All right, so y is equal to, apparently, to make this 0, I put y equal to 2/3, yeah? To make this factor 0, I make y equal to 1/2. So, of course, we got to solve 2/3 equals to sine x, and 1/2 equal to sine x. Again, for the 10th time today, we make a graph. Because we're trying to solve sine, right? And so 2/3, like up here, right? And 1/2, maybe it's here. As you can see, these pictures are not intended to be precisely accurate. They're meant to be guides for the calculation. So this, I know, sine inverse of 1/2, that's a standard angle. That's pi over 6. All right, and so this is pi. That makes this one pi minus, pi over 6, also known as 5 pi over 6. So pi over 6 and 5 pi over 6, those are two of my answers. They're how we get the half from those. This one up here, of course, is x equal to inverse sine of 2/3. And so this one over here would be pi minus inverse sine of 2/3. So the solution is x equal to pi over 6, 5 pi over 6, sine inverse of 2/3, and of course pi minus the sine inverse of 2/3. Those are all the answers that you get on 0 to 2 pi. So, yep. All right. So, moving along here. This is the next one. We're supposed to section, see if we can. So we're supposed to. Sorry. Oh man. Hopefully I have enough room here on this graph for x to go from 0 to 18. We'll see. All right. If I make, goodness, what's wrong with me? If I make this 0, 1, 2, 3, 6, 9, 12, 15. Oh, poor planning on my part. curses. 18 is just beyond. Right? All right. So my recommendation for this kind of problem is, first of all, get yourself some graph paper. Otherwise, it's just, you know, it's unfun. So at 0, we're at -4. All right. At 3, we're at -1. At 6, we're at 2. At 9, we're at -1. At 12, we're at -4, right? And at 15, we're at -1. At 18, we're at 2. So, all right, so then the question is, can you connect the dots to make a trig function? I think I can. I think it looks like about these. Now that, right, is cosine flipped over, right? So this is like minus cosine of x, right? But what's the period? We need like cosine of some number, right? Let's call it kx, such that what's the period? Well, we go from here to here. It looks like the period is 12. Because that's how it starts repeating itself. 15 minus 3 is 12. So that means that k times the period, which I'm calling x, has to be equal to, excuse me, k times 12 has to be equal to 2 pi, right? So, in other words, k is equal to 2 pi over 12, which is pi over 6. It's also shifted, right? There's a shift here. Here's the 0 line of it. So it's going down 1, right? So altogether, what I'm finding is y equals to -1 minus the, and oh, I also think about the amplitude. What's the amplitude here? It's going above and below the center line by 1, 2, 3, so I do 3 cosine of pi x over 6. I believe that'll do it. Now you can check with your graphing calculator this kind of problem, right? But in fact, that is the answer given in the back of the book. And then finally, problem 29, excuse me, you have a spring mass displacement problem. You've gotten this formula here, 8 sine 6 pi t, right? So first of all, to figure out the period, I can say, well, first of all, the amplitude is 8. I can just see that from looking at the equation. 8 goes plus or minus 8 from 0. To see the period, I set 6 pi times the period, I'll call it big T, equal to 2 pi. Solve that for big T. I get 2 pi over 6 pi, which is 1/3. So the period is 1/3. Frequency is 1 over the period, so the frequency is 3 hertz. Right. Now if you wanted, and so physicists sometimes don't want frequency, they want what's called angular frequency. So angular frequency is radians per second. Now your book doesn't ask about this, but if you were to want the angular frequency, I believe you just do 2 pi over t, 2 pi over t, and that would give you, 6 pi radians per second, I guess. It's not an accident that h of t, usually physicists use omega for the angular frequency, yeah, and so it's not an accident here that h of t is 8 sine of omega t. So that's one of the reasons angular frequency is nice to talk about. Whatever multiplies the t in the argument here, that has to be the angular frequency. So I can see directly by identification that that's 6 pi. So if you know these formulas, that's a quick way to get to other stuff. But I always fall back that it has to repeat after 2 pi. Anyway, thanks guys. Whew, just under an hour. Whew.